All right, let's use our math skills here to do a couple of quick examples and practice with the weighted average formula. If you take a quick look at guided practice problem number 1, it says silicon has 3 stable naturally occurring isotopes. These are silicon-28, silicon-29, and silicon-30. The relative abundance of each is 92.21%, 4.70%, and 3.09% respectively. Estimate the value of the answer before you begin. Will the weighted average be closer to 28, 29, or 30? Why? What is the average atomic mass of silicon? Well, based on how weighted averages work, I would estimate we will be closest to silicon-28 because it is most abundant. Boom. Now the math here, again, you're going to use that weighted average formula where it's just the mass of the first isotope, in this case 28, times its percent abundance, 0.9221, plus the mass of the second isotope, 29, times its percent abundance, 0.0470. Don't forget to move your decimal 2 places there. Plus the mass of the third isotope, in this case 30, times 0.0309. And that's it. Then it's just a matter of plugging and chugging in your calculator. 28 times 0.9221, close parentheses, plus new parentheses, 29 times 0.0470, close parentheses, plus new parentheses, 30 times 0.0309, close parentheses, enter. 28.1088 is what my calculator gives me. Again, we're going to work a little trickier here with significant figures because a lot of these are counted numbers. And we're just going to do 28.11 AMU. Again, don't fret with significant figures here in these average atomic mass calculations. Does this answer make sense? It's closest to my most abundant isotope. It's in between the smallest and largest masses. Feeling good. All right, as you take a look at practice problem number 2, we're asked to calculate the average atomic mass of magnesium using the following data for 3 stable magnesium isotopes. It looks really intense, but it's the same formula. We just have to recognize that it's important to understand the masses of a proton neutron are approximately 1 AMU. So for most purposes, like the previous problem we just did, it's really convenient just to use 1 AMU and then with these whole number mass values. However, in reality, the proton and neutron deviate slightly from 1 AMU, and the actual average atomic masses also include the very small masses of the electrons. Additionally, the small amount of the masses of protons and neutrons is changed to energy in the creation of a nucleus, way beyond what we're doing in this class. But the important thing to realize is that the actual masses of these isotopes are not quite the whole number that we would like them to be. But no big deal. As we work through this problem, it's going to be the exact same thing. We take the mass, 985 of that first isotope, that's an 8, times its percent abundance of 0.7870, plus 24.986 times 0.1013, close parentheses, plus new parentheses, 25.9, wow, I can read and write, 983 times 0.1117. So very similar process. Don't get thrown off by these new mass values. Just recognize that they're related to their whole number counterpart that they're closest to. Then it's just a matter of busting out the good old calculator, plug in and a chug in for 23.985 times 0.7870, close parentheses, plus 24.986 times 0.1013, close parentheses, plus parentheses 25.988 times 0.1117, close parentheses, solve. 24.31 sounds pretty good. 24.31. Again, don't concern yourself too much with significant figures here. Again, we got a lot of counted numbers, and we're just not going to concern ourselves too much with those significant figures in these calculations. All right, then our last problem here is one that involves a mass spectrum that came from a mass spectrometer. This particular one is showing us the analysis of the chlorine isotopes. There are two of them, chlorine 35 and chlorine 37. We are told that the intensity of the heavier isotope, chlorine 37, is determined to be 32.00%. Okay, so as we think about solving this, you need to recognize that the total percent abundance has got to equal 100. And so you can't just pull the percentages from their intensity values on the mass spectrum. What we have to do is called normalizing those intensity peaks. And to do that, all you have to do is, for example, for chlorine 35, you just take its intensity value, in this case 100, and you sum together all of the intensity values of all of the isotopes. We're going to do 100 plus 32. Okay, and when we put that in the good old calculator, all right, and when we put this in the good old calculator, 100 divided by 100 plus 32 times 100, we get 75.76%. We do the same thing for that heavier isotope, chlorine 37. We're going to take its intensity value, which we're told to be 32 out of the total intensities of all the peaks. And when we put this in the good old calculator, and you might be able to figure this out in your mind, 32 divided by 100 plus 32, close, times 100. We get 24.24%. And now we've got two percentages that when added together will equal the 100% total of all the isotopes of chlorine. This case has two. If you have three peaks, you'd have to do it 3 times, so on and so forth. But then it's just a matter of plugging into the formula, the weighted average formula that we know and love at this point. The mass of the first isotope is 35 times 0.7576. It's percent abundance, not percent intensity, it's percent abundance. Plus chlorine 37 times 0.2424, 2424. Put it in your calculator and solve. 35 times 0.7576, close, plus 37 times 0.2424, close, go. 35.48 AMU for our weighted average of chlorine as determined by this mass spectrum. Woo!